Welcome back for part 2 on our series on cellular respiration. In this video, we'll focus on the details of the Krebs cycle. At the end of our last video, we had finished glycolysis and we had taken an accounting. We had made 2 of our 36 ATP, but we hadn't gotten much else done. We'd broken glucose in half to pyruvate, and we had made 2 NADH. They're going to go to the electron transport chain. That'll be video 3. But these 2 pyruvate, they head to the mitochondria for the Krebs cycle. The pyruvic acid, or pyruvate, enters the mitochondria. But before we can start the Krebs cycle, we need to prepare the pyruvate in what's called the prep step. A coenzyme called coenzyme A binds to the pyruvate, and NADH is reduced to make NADH. In doing so, a carbon dioxide is kicked out. That's the first of those we've produced. It'll be released as a waste product of respiration. The NADH will head off to the electron transport chain, and what's left is the acetyl-CoA, which will enter into the Krebs cycle. Let's draw this in a useful way. Here's the first, or the preparatory step. We're going to prepare for the Krebs cycle. It's the molecule acetyl-CoA, a 2-carbon molecule that enters the Krebs cycle. So 1 carbon is already taken care of. Now remember, we made 2 pyruvate in glycolysis, so we have to double all of our numbers. As acetyl-CoA enters the Krebs cycle, it reacts with oxaloacetate to make citrate. Thus, the citric acid cycle, another name for the Krebs cycle. So we can draw that like this. Oxaloacetate picks up acetyl-CoA, the coenzyme A gets kicked out, and we have citrate. Now, what we have after this is a series of transfers, or a series of reactions where we're going to convert the citrate as a cycle, so we're going to get back to oxaloacetate. And in the meantime, let's look at what we produce. In the first conversion, citrate is converted into an intermediate with the input of high energy electrons, and kicks out high energy electrons to reduce NAD+ into NADH. In doing so, each citrate loses a carbon, so we make 2 carbon dioxides because we have 2 citrates. I'm not going to require you to learn the name of this intermediate, and I'll show you why in just a moment. But that intermediate is then converted into a second intermediate, and we have the same process. We reduce 2 more NADH+ and 2 more to make 2 more NADH, and we kick out 2 more carbon dioxides. Now, we need to double the numbers here for our intermediates because we have 2 of everything, so I'm going to grab a pen. I should have a 2 in front of that and a 2 in front of this. Now let's not forget the point of what we're trying to do. We're trying to make ATP, and so far we've not made any. In this next change, intermediate 2 becomes intermediate 3, and in doing so we do make our first 2 ATP, 2 intermediates to make 2 ATP, and we do this by substrate level phosphorylation. We have 2 more reactions to go. We go to 1 more intermediate, and this time we reduce a molecule called FAD+. Now FAD is a lot like NAD in that it's an electron carrier. It's going to pick up hydrogen and high energy electrons. And finally, we need to convert back to oxaloacetate, and doing that we once again reduce 2 NAD+ to 2 NADH. Now this looks like a mess, but it could be a lot worse. Here's a diagram that I found in a textbook that shows the citric acid cycle, and you can see it could be a lot worse in terms of what you're required to know for our course versus what you might need to know for some other biochemistry course or such. You can see all the names of all the intermediate molecules, which you don't need to know, but you do need to know the first that picks the oxaloacetate that picks up acetyl-CoA, and the first product made, citrate. And the reason I show it to you like this is I do want you to understand that it's a series of reactions of intermediate to intermediate to intermediate, and that it's not just a kind of a simple thing. And like I said, you don't need to necessarily know the names of these intermediates, or you don't need to know them at all. But I do think it's important to understand that it happens in stages, that we're getting this energy out of these molecules, these high energy bonds that are now in citrate that were in acetyl-CoA, that we're tapping into that energy and getting it in little pieces, and then we still have to get to that energy because we've only made 2 ATP. Now we can kind of summarize this in a little simpler form. This may be easier. If we look at it in sum total, in the prep step we're making 2 carbon dioxides, waste product, and 2 NADH, which are going to go to the electron transport chain. In this Krebs cycle, we produce 2 ATP by substrate level phosphorylation. We kick out 4 carbon dioxide, so 2 and 4, that's 6, that's all of them. We produce a total of 6 more NADH and 2 FADH2. All these electron carriers here, here, and here are going to go to the electron transport chain. There's still energy in those molecules. So all we have left to do is summarize and give an accounting. So, the Krebs cycle. Pyruvate is prepared for the Krebs cycle as converted to acetyl-CoA. 2 carbon dioxides and 2 NADH are produced in this prep step. The acetyl-CoA is picked up by oxaloacetate and converted to citrate, and then progressing through a series of intermediates, 4 more carbon dioxides, 6 NADH, and 2 FADH2s, and 2 ATP are made. ATP made by substrate level phosphorylation. And for our accounting, here we add the prep step and the Krebs cycle to this page, and let's see where we're at now. Have we used oxygen yet? Have we used oxygen? No. Have we made 6 carbon dioxides? Yes, we made 2 in the prep step and 4 in the Krebs cycle. Have we made any water? No. How about energy? Well, in the Krebs cycle we make 2 ATP, so that's 2 more we can subtract from our total, so we still have about 32 ATP to make. But we have nothing left to break down. We've taken a 6 carbon molecule, glucose, and made 6 carbon dioxides. But what do we have left to do? What can we still tap into? Well, if you can see along the way, we've been picking up NADHs, 10 of them, 2 from glycolysis, 2 from the prep step. Here we go. Oops, let me turn my pen over. 2 from glycolysis, 2 from the prep step, 6 from the Krebs cycle, plus these 2 FADH2. All of these molecules are going to be sent to the electron transport chain for electron transport phosphorylation. There's still a lot of energy that we have to tap into in these molecules. In fact, the majority of that energy. And notice we've yet to use oxygen and we still haven't made water, so there's a lot more to do. So come back to the next video on electron transport phosphorylation. You can find the link here.